Since beams will generally only have small deflections and therefore small curvatures, we can use this expression for beam curvatures. And it also turns out that we can link the expression for curvature to that of the bending moment within a beam, say m of z, with a constant e and I, which are geometric and material constants, as in the expression there. This is useful because this is an expression which, if we can integrate it twice, will give us the deflection of a beam. So to see how this works conceptually, we'll work through the maths, and then we'll apply it to an example. So here we've integrated once, and we see that we've now got dy by dz appearing in the equation. Now, dy by dz is the gradient of a beam, so this in itself might be useful. If we integrate again, then we get an expression with y, and it's y, the deflection of a beam, that we're looking for here. There's 2 points to notice at this point. One is that we've got two unknowns in our expression, a and b. These are constants of integration, and we'll need to find out what those are. We'll come to that in a moment. The other one is that we've used z as the horizontal beam axis and y pointing downwards to measure deflections. This is quite common for beam deflections because we want positive deflections to be downwards because gravity tends to act downwards. Some textbooks and some computer programs take the normal xy axis used for most of the maths. In that case, we wouldn't.
And is equal to WL divided by 2 times the distance times x. And now the contribution of the load, in this case, this is creating a moment here like this. Therefore, the internal reaction goes like this, and this is negative. So this is negative, and the magnitude is equal to the, well, this is a rectangular load. So first, the area of this load, which is equal to x times w, and the distance is the distance from the centroid of this area to the point x. So this is x divided by 2 times x divided by 2, then this is equal to WL divided by 2 times x minus WX squared divided by 2. Then now we need to calculate what is the curvature of this beam. So we can use moment curvature relationships. We have that the moment is equal to minus EI second derivative of V dx. So we can integrate here. Therefore, we have that m is equal to, as we said before, then if we integrate here once, we have that EI dV dx is equal to where a is the constant of integration, and of course this is equal to the slope theta. We can integrate once more. Then we have one equation for the slope and one equation for the deflection, and now we need to determine what are the constants of integration. So we can use boundary conditions. We have that the deformed shape of this beam is something like this. So it is symmetric. Then from this symmetry we have that at this point, at the midspan of the beam, we have that the slope